All right. Welcome back. Let's get started. So today I want to talk about cache. A lot of things to discuss, so let's get started. Probably you've seen that the grades were out. I posted the grade distribution as well as the actual rubric that we used. They are all in the same post. So like the first link is the Google Doc for the rubric, and the second one was like the picture was the grade distribution. I think the average was pretty good, like 88 something. So good job, guys. And for those of you who didn't do well and below average, don't worry, there are other opportunities for you to kind of catch up, right? So the reason that we have multiple quizzes and other things is for you to kind of stay engaged for the entire quarter. So there are opportunities for you to kind of like do better in the second and third quiz and get a good grade. So don't get discouraged, continue working. And I mean, there were problems with, that you might have some problems with the logistics, with the style of the quiz and so on. So hopefully in the second and third quiz, you might do a little bit better. Now you're more familiar with the setup. If you think that there is a mistake in your grading, you can always check the rubric and then submit a regrade request if you think that it's not consistent with the rubric. We're gonna definitely go over it, and if there is any mistake, we will fix it. The procedure for this is that on the grade scope, you have to submit a regrade request. The original TA who graded that homework will go over it and then fix that for you if there is a problem. If there's like a very specific scenario that they're not sure about, they will consult with me, and then we're gonna make a decision. We try to actually give you a lot of partial grading. But I mean, if there is still, you think there is something that you're missing, let us know. We're happy to look at it. Okay. Homework 4 is also extended to Sunday, just given that, you guys are a little bit busy. Homework 5 and project 2 will be also released soon. And what we're going to discuss today is basically going to be end of what we're going to cover for quiz 2, which is not this coming Tuesday, but the Tuesday after. So what we're going to discuss next week is not going to be part of your quiz 2. It will be part of quiz 3. Any questions? Everybody signed in? Good. All right. So last time we discussed memory hierarchy, right? We told you that essentially the idea is that let's have multiple layers of memory, and with this we're going to have this illusion that we have a very large and very fast memory, right? The reality though is that the cache is significantly smaller than the memory. So we kind of need to decide on what sort of structure, what sort of mapping are we going to use in our cache, right? And as I said, since there are many, many lines in the memory, but many, many less lines in cache, of course, there will be multiple lines in the memory that will be mapped into the same lines in the cache. So for example, all these gray lines will go into this one, all these blue lines will go to this one, and so on and so forth. And the idea is basically you're gonna, at each time you're gonna be able to store only one of them, right? So they're gonna kind of kick each other out. And then at any given point, you're only storing one of these memory lines. In order to kind of like find the structure, we talked about various different structures. We talked about direct map, which the idea was basically using some part of the address as the index and kind of index that table. And once we know that this is basically the kind of the address, this is the line that we need to go to, just go and put the data there. And then we did a little bit of optimization, said that, okay, if this is my entire address, I use some of it for the index, but since I need to kind of distinguish between different lines, I need to also store the remaining part as a tag. So essentially, I'm going to my cache structure is essentially two things. There's a tag store and there's a data store. The data store is obviously for storing the data. That's the primary use of the cache. But since the way that we are kind of storing this requires some form of tagging, we also store the tag. And for this particular example, for example, it was only 1 bit for the tag, but in some other cases, this could be more, right? Then we talked about alternative to the direct map structure, and specifically we talked about what we call fully associative. The difference between fully associative and direct map was in fully associative we don't care about the indices. We just say the first available position, and then we're gonna go and put the data there. Basically, the difference is like when you're coming into this room, you either have an assigned seat, which is like, I don't know, row 2, like, chair number 103 or 104 or whatever, right? So everybody knows exactly that where they're going to go, versus the fully associative one is basically you just come to the class and see what is the first available seat that is good for you. You go and sit there. So that's the difference between direct map and fully associative. Since we have no idea where each data is, we essentially need to use the entire address as the tag. So that's kind of like the trade-off that we are making when we're having a fully associative cache. We also talked about this thing called average access time. And essentially we said that the main thing that we care about a cache system and memory system is this average access time. So this average access time is basically, if you think about the CPU on this side and my memory system, which is the cache and my main memory on this side, what CPU really sees is this average access time. How much does it take on average for bringing 1 byte, for example, of data? That's really what we care. And then we talked about how we actually drive this. So essentially the average access time is combination of hit time, which is the time it takes for us to go through the cache and search the cache. Plus, if the data is not in the cache, then we need to go to the main memory and search the main memory, and then inside the main memory, if the data has to be there. So that would be basically the time it takes to bring the data from a main memory to the cache. We call that miss penalty. And then how often from the cache we need to go to the main memory, that's what we call the miss rate. Let's see. Okay. Oops. Any questions so far? We clear? Okay. Stop working. So what I'm going to show you now, once this actually loads, is showing you the difference between direct map average access time and fully associative average access time. And I mean, once this is loading, let's go over the hit time, miss rate, and miss penalty. So first of all, what do you think is the difference between the hit time of fully associative versus a direct map? Who thinks that direct map has a faster hit time versus fully associative? Okay. And the other thinks that fully associative is faster than direct map. Who thinks it's actually they're equal? Okay. There are some people. Let's see. Okay. All right. So let's so hit time. The first question is, which one is faster? Is it fully associative, less than direct map? Is it equal? Or is it direct map is actually faster? Anybody wants to explain why they think that fully associative is faster than direct map? Or the other way around? Anybody who wants to say why direct map is faster than fully associative?
Exactly where it's going to be. Based on the context.
Like
we can instantly look for it for fully associated.
Yeah. So, yeah, exactly. So the comment was, if you think about the hit time when the data comes, for direct map, as I said, we exactly know where the data is stored. So we can just basically just go there and check the tag. For fully associative, that's not the case. You have to check the tag for every single row. And not every time the first row is the row that it's a hit. It might be the second row, or third row, or fourth row, right? So obviously the hit time of a direct map is significantly lower than the hit time of a fully associative cache. Okay. What about miss rate? Which one do you think has a better miss rate? Any suggestion? Yeah. Fully associative has better miss rate. Why?
Because you're always making sure that you're using up all the space in the cache.
Yeah. So fully associative is going to have a better miss rate because you utilize your cache better, right? You make sure that the entire cache is full before you're taking something out. Versus direct map, if the addresses are conflicting, then the direct map not going to perform very well. So fully associative technically can have a better miss rate. Okay. And what about miss penalty? Which one do you think has higher miss penalty or equal?
They're probably equal because it's just accessing the slower memory, which is the same default.
Yes, so their miss penalty would be the same because miss penalty is not about the current layer, it's about the next layer, right? So in both cases, because of the miss, we have to go to the main memory and we have to bring the data back. So it doesn't matter whether you're using a direct map or fully associative or any other method. The miss penalty for all of them are the same, okay? So this is kind of like the summary. The hit time for direct map is much lower than fully associative. The miss rate of fully associative is actually smaller than the direct map, and the miss penalty is the same. Okay. Anybody has any doubt or questions why this is the case for these three? Yeah.
So I think in the last lecture you said that hit times are the most important measurement for that, and that direct map is like.
So the question is, last time I said hit time is more important than the others. Does that mean that the direct map is needs to be used? Yeah, kind of, yes. We're actually going to talk about the improvement over all of them, but usually our like first layer of cache is some form of direct map cache. Actually, in the next slide, I'm going to show you something in between of these two, and then that's what we usually use actually. All right, so given this kind of trade-off that you can see here, it seems that the hit time for one is better than the other, and the miss rate of one is better than the other. So the natural question is, can we have both? Can we have a mechanism that has, good hit time, same as direct map, and has a good miss rate, same as fully associative? And that's the idea of what we call a set associative cache. So the set associative is kind of like a combination of a direct map and fully associative. Essentially, what we are doing is that we are adding associativity to each line or each what we call set. Okay. So basically, if you remember, direct map was like this, right? So we had indices. The indices basically tell us which line to go, and then we had tag to store. Then we also had fully associative, which basically says that I don't care about the indices. Let's just use the tags. So the set associative is kind of in between the two. So basically what it says is that let's have some form of index, but within each index, let's have the option of just choosing whichever I want, okay? So for the same example, let's say we have a 3-bit. Set associative essentially gives you, instead of like having 4 lines that we had before for direct map, set associative says that, okay, let's have only 2 lines. But within each line, let's have 2 options. Let's have this row and this column and that column, okay? So essentially the idea becomes like this, that, back into the class analogy, I told you that, for example, let's say your seat is known. For example, you're sitting in the 2nd row and the 3rd seat from on that row, right? Set associative, and then fully associative is basically there is no assigned seat, just go and free for all, sit wherever you want. So set associative is like this, that you know which row you're going to sit, but you don't know which seat within that row. So whichever seat is available in that row, you're going to go and occupy. Okay, so this is kind of the idea of the fully associative. So we still have the index, okay, and the index basically tell us whether to pick this row or this row. But within each row, we have multiple columns, in this case, 2 columns, and the data can choose any of these 2 columns. Okay, so either can go to the first one. If the first one is free, is not free, it goes to the second one. If second one is not true, it goes to the first one, and so on and so forth. Okay. And as you can see here, for set associative, we still have index, but our index is only 1 bit because there's only 2 lines, right? There's 2 different rows. If you go back to the direct map, the index was 2 bits because there were 4 lines, right? And then for fully associative, there were no index bits because there was no difference between the rows. Okay. And you can actually see how set associative is kind of in the middle ground between the two. So if you don't have any row, if you don't have any column, you just have one column, essentially your set associative is the same as a direct map cache, right? So the direct map cache and set associative cache is the difference between them is that set associative has multiple columns versus the direct map has just one column, right? Or in other words, fully associative and set associative, the difference between them is fully associative is just one big row versus set associative is the multiple rows with less columns, right? So that's kind of like the trade-off between them. So we call each of these columns bay, okay? And we call each row a set, okay? So for example, this cache is a 2-way set associative, okay? When we say 2-way, it means that each row has 2 columns. If it's like an 8-way set associative, it means that we have 8 columns per row. And then combination of multiple rows, we call this a set, okay? So the cache set number 1, number 2, 3, so on and so forth, okay? So within each set, we have a fully associative cache in some sense, right? Within each set, there is no difference between each column. But between the sets, there is the index that decides which one it has to go, okay? So this is kind of like the actual architecture of set associative. As you can see, for example, this is a 2-way, okay? So there's one way and there's another way. Actually, it's more of like this. This is one way, and this is another way. And as you can see, each way has its own tag store and its own data store, okay? So how do we actually look up? So the lookup is like this. For example, if it's a 2-way set associative with 8 lines, we need 3 bits to kind of address this. So the index selects which row to go to. Let me actually delete these. So for example, let's say my index in this case is 1, 1, 1. That means that I select the last row. But as you can see, since this is a 2-way set associative, there are 2 possible tags that I need to check. I check both of them in parallel, okay? So I check this one, and also I check this one. And then if either of them is a hit, then I say this is a cache hit, right? So because your data might be either here or there, either of them is a cache hit. And then I'm going to bring the data based on whether this one was equal to 1 or whether this one was equal to 1. And that's where I'm going to get my data, right? So basically, if you remember in direct map, I only had one set of these tag store, one set of these data stores. The index just go and grab the data from there. In fully associative, I basically need to go through every row and check. But for set associative, I first select the row. Within that row, I need to check all of them. So in this case, since this is a 2-way, I only check 2 different ways, 2 different cache, tag stores. Does that make sense? Yeah.
We stop checking as soon as we find a match.
The question is, do we stop checking as soon as we find a match? Yeah, of course. But this happens in parallel, so there's no sequential events that you say that we stop, right? So the address comes, you pick the index, you go to that index, and then you in parallel check. So really, they're happening exactly at the same time.
Yeah, for the columns, assuming that, not for these columns, the one in the slide before, if we fill up both columns, we kick out both entries, right, and then start refilling it?
The question is, if we fill out both columns, then what should we do? Actually, we're going to talk about this in this lecture, but no, you just kick out one of them. You don't need to kick both because they're independent from each other. Yeah.
So the number of columns, the more columns you have, should that mean the higher the time, the less of this
Yes, that's a great observation. So the more columns that we have, then we're gonna have more hit time. So the more column you're getting closer to fully associative. The less column you get closer to the direct map, right? So that's, but the more columns you probably get a better hit miss rate, right? So you had a question?
Yeah. Do the data accesses happen in parallel with tags?
Yeah, the question is, do the data access actually happens in parallel with the tag? Yes, we always do this in parallel. That's why I think I'm here also showing. So you always check them at the same time. If the data match, then you send out the data. If the data is not matched, this is a cache miss. You have to go to the memory. Questions? All right. So let's actually do another example of what we had before. If you remember, we had like a pattern sequence like this, 080808. And if you remember, for direct map, we keep having the miss because 0 and 8 maps into the same row, and we always had a miss. Fully associative actually didn't have a miss at all because we can just assign 2. But the problem fully associative is that fully associative has a very low hit time. But let's see actually what happens with the set associative in this case. So again, let's assume that we have an 8-bit address. Okay, and let's say we have a pattern like this, 080808. So first of all, what would be the tag size for the direct map? If you have 8 rows, what would be the tag size for direct map? Anyone? Yeah. What's that? Tag size would be 3? 5. Yeah. So we have 8 different rows, right? So that means that my index is 3 bits. And then since I have 8-bit address, that would be 8 minus 3 would be equal to 5. That's my tag size for direct map. So here data goes into 5 bits. And then now question is, what is the tag size for set associative? Anybody wants to compute that? What's the tag size for set associative? Someone? Yeah.
Is it 6 because we have 4 rows?
Yeah, it would be 6. So we have 4 rows. So now this time my index number of bits for my index is 2. Still, I have 8-bit data. So that means that my tag is 6. So my tag size, of course, grows because I have less number of rows, so more tags. So the difference between direct map and set associative is that the size of the tag are not the same. Okay. Any confusion on how we come up with 6 and 5? All right. So let's see what happens with the address. As I said, the way to kind of solve this problems is that you have to convert this into binary. So 0, 0, 0, 0, 0, 0, 0, 0. And for 8, it would be 0, 0, 0, 1. And 0, 0, 0, 0, right? Then you have to divide this into indices and tags. For direct map, as I said, the first 3 bits would be the index. Okay. So basically both 0 and 8 map into the index 0 because the lower 3 bits are the same. For set associative, the lower 2 bits is the one that we are checking. So in this case, it's this 2 and this 2. And again, they map into the same row, right? The difference now is the tag. So as you can see, the tag here in this case is this top 5 bits, which is equal to 0. For this, the tag is top 5 bits, which is equal to 1. So the difference between address 0 and address 8 in a direct map cache is that they map into the same index, but their tag is different. The tag for 8 is equal to 1 because their upper 5 bits is 1, 0, 0, 0. And then the tag for bit 0 is 0, right? And then what is the tag for set associative? Anybody wants to guess that?
0 and 2.
Yeah, 0 and 2, right? So why 0 and 2? Because if I put it here, so it would be 0, 0, 0, 0, 0, 0, 0, 0. So basically this 2 bits is the index. What remains is my tag. So in this case, the 6 bits is 0. the 6 bits is 2, right? So the tag for 8 is 2, the tag for 0 is 0. Okay, so this is how we actually gonna sort things here in my cache. Any questions before we actually populate the table? Yeah.
I'm gonna set associated when both of the index zeros are populated and the new instruction comes along. Since everything's in parallel, how does it decide which one to keep out?
So the question is about like if we have like 2 rows and we don't know which. Oh, I'll talk about that. I'll talk about that. All right, so let me actually then kind of like go through this. So now that I know the tag and the index, so for the direct map, here's would be the sequence. The sequence would be I put the tag 0 here, then 8 comes, the 8 has tag equal to 1, and since I stored 0, I need to kick this out and put 1 here. So there will be the first one will be a miss, the second one will be a miss. Then 0 comes, I stored 1, I need to kick it out and put 0. So this one would be a miss. 8 comes, again, I stored 0, now I need to store 1. And so basically all of them will be a miss because we always kind of like storing the previous one and they kind of conflicting each other. For set associative, the 0 comes and I put tag 0 here. Then 8 comes, it goes to the same index, but I see that this line is actually like this column is this way is free. So I don't need to kick this out. I put tag 2 here, right? Because 8, I just show you how it's to tag 2. So the first 2 will be a miss because I didn't store the data. The first 2 are a miss. But then when the third 0 comes, I already have the data, right? So it will be a hit. Now the 8 comes, I have the data, it's a hit. 0 comes, it's a hit. Again, 8 comes, it's a hit. And if you remember, I showed you this for fully associative, and for fully associative, it was also miss, hit, hit, hit. Okay. So set associative and fully associative in this particular case match exactly the same, right? So as you can see, I have a set associative cache that performs equally well with a fully associative in with this particular example. But the hit time is very, very shorter because I only check 2 things versus in the fully associative case, I had to check 8 things, right? So 4 times faster, almost equal to direct map, but much better performance in terms of mystery. Okay? Any question? Yeah.
Seems that the set associative architecture is like in map implementation, different pockets that for mine, it's like similar if they have any relationship.
The 2 different ways. Yeah, so the question is, what's the relationship between these two? It's just they're completely independent. So think about it as kind of round robin. We put the first one and second one for first one, second one, and so on and so forth. So within, again, like think about the classroom, within each row, let's say there are 10 different seats. There is no difference between each of these seats. So the only thing that you should do is that for example, you're sitting in the 3rd row, but you can pick any of those seats, okay? Versus for direct map, you know exactly you had to sit there. That's the difference.
So we access them also in parallel.
We access them in parallel. Yes. All right. I don't know why I have it here. Oh, okay, yeah, there you go. This is another problem for you guys to take a look. So this is slightly different access pattern, and maybe you can take a look and see whether this one is also benefit from that. And again, so probably someone can put it on the campus wire. I'm gonna give you like 2 minutes to think about this, write it down. So same thing, 8 rows, 8-bit address, all the things is the same, just the access pattern is different. The first person who submit on campus where will count. I'll remove others. Sorry. Of course, you can post because there might be different answer. I'll remove. All right, so let's continue. So this is kind of like the idea of associativity in the cache, right? So essentially, you know, if you have a tag store and data store, the direct map is essentially telling you that you know exactly where you search. The set associative, if for example this is a two-way set associative, means that you have to do two parallel access and two parallel search. And the fully associative tells you that you basically needs to go through the entire number of sets or rows that you have in order to find them. Sometimes you might get lucky and find it here. Sometimes you might get unlucky and you need to go all the way through the entire set to find, right? So that's kind of the idea. So let's go back to the DM FA and SA, which is direct map fully associative set associative, and let's talk about the hit time, miss rate, and miss penalty of these three together. So let's see where set associative sits between them. So hit time, where is set associative? Suggestions. Set associative. Is it better, worse compared to the other two? Yeah. In the middle, right? So set associative sits in the middle, very close to the direct map, but far away from the fully associative. Okay. What about miss rate?
It's still be similar to fully associative, but still be in the middle.
Yeah, so it's still in the middle, but closer to fully associative this time. And miss penalty? The same, right? So I told you there doesn't matter which one we use. Okay, so it's kind of like this. Just pay attention to this kind of like, you know, notation I'm using here. That set associative and DM is actually very close to each other in terms of hit time. And then the miss rate is closer to the fully associative. And somebody asked at the beginning of like for what we are using. Basically, we are using set associative in most of our cache. So almost all modern systems use set associative cache. They only use direct map if they really need a very fast hit time. Otherwise, almost all standard systems, all of your laptops and any cache that you have, all of them use a set associative cache. Okay, usually 8-way or 16-way. I'm actually going to talk about why we don't go higher than that, but we usually have an 8-way or 16-way set associative cache. You actually can search your model of your laptop, for example, your CPU, and see which type of cache you have. They usually actually have the actual, you know, numbers for you as well if you want to see that. Any questions so far? Okay, so now let's talk about this questions of, okay, now we know the structure, now we know how to kind of what we call install the line. Well, of course the cache at some point get full, right? And for all these different structures of fully associative, set associative, and direct map, the question becomes, how do we actually kick things out and replace it with a new thing, right? And you already asked that question, so let's actually go through that and talk about it. So essentially the idea is what happens on a miss. And let's say we have an address sequence like this. If you look into your direct map, it would be something like this. Sorry, they'll all be zeros actually. So I'm going to store tag 000000000 here for these addresses. Their index is different. Now address 8 comes. In direct map, what we do is that since we know the direct map maps here, we need to kick this out and put 1. So for direct map, this is pretty straightforward. There's only one solution and one place that the data can go. if data is not there, we're gonna kick whatever is there out and replace it with this new data. For direct map, we don't have really any problem. But the question is, for example, for something like fully associative, we actually have something like this now, right? And now this address 8 comes. And as I told you, the address 8 can go anywhere because we don't care about the index. So this question is, which one of these should I kick out, right? Should I kick out this first one, this last one, somewhere random in the middle, and so on and so forth? Which one should I kick out? And the reason that it's very, very important which one is kicked out is if you consider something. So first of all, kicking out, we call it evict, okay? So eviction means that we kind of like, kick it out. But the important thing is that it's very, very important which one we evict, because consider it's like a pattern like this, that I have 0 to 8, and very, very soon after that, maybe after a few other addresses, 7 shows up again, okay? And then if you go back to this kind of like example that I gave you, the difference here is that if I had decided to kick out 7 when 8 comes and put 8 here, then the next 7 would be a miss, right? Alternatively, if I decided to, for example, kick out, I don't know, 0 and put 8, then 7 would be a hit, right? So my eviction policy, my what we call a replacement policy, has a significant impact in future miss rates that I have. If I do this intelligently, then I potentially can minimize the amount of miss rates. If I just do this, on the fly randomly, then I might suffer from miss rates. And the important thing is that I don't have the information about future, right? I don't know which address is going to come. If I had known, of course, I would have, not evict that data. But I need to make a decision about future based on just the past activities, okay? So this is the story of what we call replacement policy. And again, for set associative, we're gonna have the same issue similar to the fully associative. In this case, we're gonna have 0, 0, 0, 0 for these 4. Then I'm going to have 1, 1, 1, 1 for this 4. Then 8 comes, and I know that 8 needs to go here because the 8th index is here, but the tag is 2, right? So now the question becomes, out of these 2 possible, rows or columns, should I kick this out and put 8 here, put 2 here, or should I kick this out and put 2 here? And again, it matters because if I kick this one out or this one out, if in future, for example, 4 comes, and then I already kicked that out, that become a miss, okay? So set associative is a little bit better than fully, but still a big problem in terms of what to kick out in order to make sure that we optimize the performance, okay? So let's talk about this question. So what to evict when there is a miss, when my cache is full. And again, the only thing that we need to care about is for set associative and fully associative, because I already told you that for direct map, there's only one option, so we don't have a choice. We just kick that out, right? But for fully and set, we have options. For example, if it's a 4-way set associative, we have 1 out of 4. If it's like 8 rows fully associative, we have 1 out of 8, and so on and so forth. So we need to make that decision, okay? So the first thing that we can do is we just pick at random, right? So we don't know, we just, select something at random, like one of those 8 lines, and say, okay, I'm gonna evict this, and then that's it, right? The good thing about picking at random is it's very, very simple, right? Because I don't need to store anything, I don't need to remember anything. The fastest way of doing this. But of course, the problem with this is that we're not really using any information from previous activities, and I'm not really using what we call temporal locality. And if you remember, I said temporal locality is actually quite important for us, because temporal locality is that if I access something, for example, if I access this line, very likely in future I'm going to access it again. So it's our best interest to keep that in our cache. Okay. So what are the other options? Anyone wants to suggest any other way of kicking things out or replacement policy? Yeah.
Replace the old sentence. You can replace the old sentence.
Yeah. So you replace the oldest entry, right? Whichever came like the oldest, you kick that out. That seems to be one good thing. Yeah.
Keep a history and like count the occurrences of like each thing and kick out the least used.
Yeah, so you keep entry of how many times each of these lines has been used, and you kick the one that is the least recently used. So you essentially don't necessarily kick out the oldest one, but you kick out the one that is the less popular. Any other suggestions? You can also do things like FIFO, first in, first out. You can do last in, first out. You can do all those other things as well, right? But yeah, so the ones that is the most popular and being used in almost all of the designs is what we call the least recently used, or LRU, right? So the idea is that let's find the oldest, and in this oldest, I mean the oldest used one, not the oldest that's been installed, but the one that has the less amount of usage, and evict that. The reason for this is why? Why do you think this would work? The reason for this is that I'm going to say that I'm going to bank on this fact that I'm going to use a lot of temporal locality, right? So if things are being used a lot, it means that it's going to be used again and again and again. If things start kind of like cooling off and it's not really being used anymore, then among the choices that I have, this seems to be the best option, right? And one thing to keep in mind is that there is no optimal solution here. You can make an incorrect decision. You might, for example, decide LRU, like, you kick out the least recently used one, and then that happens to be actually a bad decision. But what is happening is that on average, this is a very, very beneficial decision to make, because in most cases, you have temporal locality, so this is actually going to be paid off, okay? So how do we actually implement LRU? We need some form of storage to kind of keep track of the number of usage for each of my lines, right? So the downside of LRU is that it's more complex and required extra storage, because I need to kind of keep track and keep tab on who has been used, how many times, and then I need to know which one is the least recently used. So how do we implement that? We add this additional column to our rows called position, okay? I mean, different people call it different, but in this class, we're gonna call it position. And the position, it basically tells you that which one is the least recently used, which one is the most recently used. We usually use this notation that we start from 0 all the way. For example, this is 8 different rows, so we start from 0 to 7, which this is the oldest. So basically what we need to do is, if we want to kick something out, we're going to find which one is 0, and we're going to kick that out of our cache, okay? So how does this work? And by the way, your project 2 about implementing a cache and a replacement policy. So this is what you're going to implement in your project. So let's say, for example, we have something like this. And let's say that this is a fully associative cache for simplicity. So what we're going to do is, let's say we have something like this. So we're going to put one, let's say, for example, the cache is already pre-populated and I have something like this, okay? So basically what I have here is that I had a sequence of 1 to 7, and then I'm going to have this sequence here, okay? So this is the initial state of a cache. For now, we don't need to pay attention to the data. So data is, I just show it that it's there, but we're not really using it, okay? So let's see what happens here. For LRU replacement policy, what we are going to do is that we're going to see the first data that comes, and this one is 1. So one is already stored here, it's here, so it's going to be a hit. What we need to do now is that we also need to update the position of one because it has been used, right? So not only it's a hit and we need to kind of forward the data to the CPU, we also need to internally update the status of my lines, okay? So in this case, this line 1 has been used, so I need to update this position. This used to be position 1 before the oldest, and now it's very, very recently has been used. So I need to, what we call, promote the position of this line into the LRU, actually. Sorry, to the MRU, or most recently used one. Okay? So what I need to do is that I need to update this position table, and I'm going to write it down here. So I'm going to put this into position number 7. The reason I put it in position number 7 is that the very recent one is being used, so I need to put it on top of my list. Since I put this one to 7, then everything else needs to be also adjusted accordingly. So what used to be 7 now needs to be 6. What used to be 6 is 5. Now it's 4. Now it's 3, 2, 1. And this one is before. It used to be 0 and it stays 0, right? So it was before 1, it stays before 1. So now my position is this new one here. So that now my line 1 is at what we call the MRU position, or the most recently used position. Okay? Now this 2 comes, and then again I see that 2 is here. So it's going to be another hit. And I again needs to update my positions. How do I update my positions? I make this 7, I make this 6, this stays 0, this goes to 1, 2, 3, 4, 5. Right? So I update my positions. Any questions so far? How do we did this? Yeah.
If you use the entries, is it possible for 2 different entries to have position 0?
No, it won't be 2 possible entries to have position 0s, right? So the question is, why don't we have 2 zeros? Because, like, remember a scenario like this. This one was 0, this one was 1, right? But this one is updated back to position 7. If, for example, at some point I access this data 0, this one will go to 7, and then what used to be 1 is now 0.
What, instead of accessing 1 the first time, what if you had access like 6, and then decommitted everything else? Would it then do 0?
No, because again, 6 is, so think about this as kind of like 8 people in a line, right? So you pick someone out and put it in the front of the queue, everybody else just go 1 down, right? You never, like, 2 people don't go to the, there's always an end of the line, that so you never have like a scenario where you just, everybody just go 1 step back, unless they're behind the guy already. So if I'm like in the middle of the queue and go on the front of the queue, then everybody behind me stays behind me. They don't need to go 1 step back, right? Any other questions? So this continues, right? So 8 comes, and one thing that is happening is that 8 is not in this table, right? So this would be a miss. And now I need to replace something. What should I replace here? Any suggestions? I should replace the one that has position 0. In this case, it would be this line. So I get rid of this and put 8 here. And another thing that I need to do is that I need to update my positions. So even on installing a new line, I need to update. Okay. So what should I do? So this one that used to be 0 now is 7. It's 7. And then everything else just has to go 1 down, right? So this would be 6. Sorry, 5, 6, 0, 1, 2, 3, and 4. And then what I have done is just I get rid of the tag 0 and replace it with tag 8. Now 9 comes. 9 is also not there. Another miss. What should I kick out? In this case, I'm going to kick out whatever this is, right? Because this is now my least recently used. As you can see, I don't kick out 1, I don't kick out 2. Why? Because 1 and 2 has been recently used. By 3, now 3 is my oldest line, right? So I kick out 3, I put 9 here, and then again I update everything. So this has to be 7, 5, 4, 6, 0, 1, 2, 3, right? And the story continues, right? One thing to note is that at some point, for example, 3 shows up again. And unfortunately, at this point, we already kicked this out. As I said, LRU is not a perfect solution, but it's just a good solution. In most cases, it works really well. Question? So the question is that this recalculating the position, wouldn't this be very slow? It will be slow. I mean, it wouldn't be too slow. It's just 8 lines, so you can do that. But keep in mind that this happens in the background, right? So the request from the CPU comes, and we quickly check the data, and the data is either there or not there. If it's there, we're gonna forward it back to the CPU. And then this update happens after that, right? So you forward that data back to the CPU. Now you need to internally kind of do some form of a bookkeeping. You need to update that, right? So this happens in the background, so it doesn't have any impact on your AAT. Your hit time stays exactly the same as before. This is just something that happens after. Any other questions? All right. So I don't do the rest, but you can definitely do the rest and see how this would be get updated. But essentially the idea is on a hit or on a miss, we install a new line or use the same line. We promote that line to the MRU. We always do that. Okay. So don't forget to do that when you're implementing this. So the only problem with LRU is that it's very costly in terms of storage, because I need to store like a 3-bit value per row in each case, because the positions are kind of like I need to store the positions, I need to keep track of positions and all those things. So it's costly, especially if I have many rows, right? Because I need many bits for each position. I need to go through every position. So in terms of implementation, it works great, but it's pretty costly. Okay. So a minor optimization in order to fix this is what we call a pseudo LRU algorithm, or PLRU for short. And the idea of the PLRU is that we only use 0 and 1 for the positions. Okay. So we either, like, since we only need to find the least recently used, I'm just going to use 1 bit to kind of like indicate between things that have been used and things that haven't been used. Okay. So the idea is this, that instead of the position, now I have what I call a flag, or you can still call it position, but the position can now only gets 2 numbers, either 0 or 1. So it's just a binary value. Okay. We start with all zeros. Okay. So initially everything is zeros. But then if the line is being used, or if we install a new line, if the line is being used, not when we install, if the line is being used, we change that flag from 0 to 1. Okay. So for example, if line 0 is being used, I change that flag to 1. Okay. So on a hit, we set the bit to 1. On a miss, we're going to find the first line that the flag is 0. Basically, this tells you that this line hasn't been recently used. Okay. How do you find that? We start from the top and we go down. Okay. So for example, if the scenario is that like this one is 1, this one is 1, and maybe this one is 1 and this one is 1, the line that we're going to kick out is going to be this line. So we start from the top, we go down, we check the bits. The first one is 0, we kick it out. Okay. If all the bits are equal to 1, okay, so there will be a scenario where, for example, a hit to this one, hit to this one, hit to this one, and so on and so forth. So all the lines become 1. In that case, we cannot kick out anything. Once all of them become 1, we're going to reset them back to all zeros. So if all of them are 1, then we reset them back to all zeros. Okay, and then if the new one comes, we kick out the first 0 that we find, and that's it. Okay. So basically, this is the idea of pseudo LRU. Very, very simple. It doesn't perform as well as LRU because it cannot distinguish between the timing difference of multiple of them, but still is great for catching things that are really, really old. Because, for example, if you have a sequence of data and then some of them are being used, frequently, and then there's this one line that's not being used, what will happen is that your flags are becoming like, most of them becomes 1 and maybe 1 or 2 of them become 0. And then if you want to install a new line, you can go and find that line and boom, you can replace it with the data, right? So the advantage of this is that it's very simple to implement. You just basically just need 1 bit per line. Very scalable because it's not dependent on the number of rows. If you have 200 rows, it's still 1 bit. If you have 8 rows, it's still 1 bit. And the algorithm is also very simple. On a hit, I'm going to put 1. On a miss, I find the first 0, kick it out, replace it with a new data. You have a question?
Wouldn't this be time costly in the case you didn't check every single bit?
Would it be time costly? Yes, it would be a little bit time costly in order to find which one, but it's the same thing for LRU as well. Because for LRU, I also need to go through the whole positions and find the first one is 0. I don't know which one it is. So it's the same thing. But again, it's usually like there are ways to make this as fast as possible. Any questions? PLRU is what we use in most of our modern processors. We almost never use LRUs. What we do use in almost all the processors is PLRU. There are different ways of implementing PLRU. There is a tree-based PLRU and there is an NRU-based LRU, pseudo LRU. This one that I showed you is what we call not recently used or NRU-based PLRU. Intel and others also use another method called the tree-based. If you just search, tree-based in Wikipedia, you're going to see the idea is pretty much the same as this one, but both of them are just using 1 bit in order to decide whether or not this line has been used or not. But just one thing I want to emphasize is almost all of our modern processors and modern caches use PLRUs, not a real LRU. Yeah, question.
In the set associative cache,
Mhm.
would there have to be some sequential logic so you don't replace both at the same time as both like with 0 in the 2 columns?
So the question is on set associative, if you have 2 columns, how do we decide which one are we? So think about the columns as the rows here. So if you think about this so this would be your column 0, this would be your column 1, this would be your column 2. Again, you start from column 0, you find the first 0 and you kick it out.
So that's not done in parallel.
For kicking out, no. So for kicking out, this doesn't happen. So generally, for kicking things out, you do it in the background. You don't need to do it in parallel. You just go 1 by 1 and you kick it. You first search. Your search happens in parallel. If you see that there is a miss, it means that now I need to kick something out to replace this data. So which one should I replace? I go through this list and I replace. Any questions? You're going to implement this as well in your project, so you're going to learn a little bit more. So generally, this was what we called replacement policy. And if you pay attention, there was 3 main things that we do in a replacement policy. We called it install, update, and replace. Okay, so these are the 3 questions that we kind of answered when we were designing a replacement policy. For install, the question was, where do we put a new line, right? So for example, in LRU, we find the position 0. In pseudo LRU, we find the one that is flagged 0, and so on and so forth. The update is when we are saying that what happens if there is a hit. For example, in LRU, I told you that you need to promote the position of your LRU to the most recently used on a hit. So that's the policy that you're using. And of course, the replacement is what we really replace. Which one do we replace? So for example, in pseudo LRU, we find the first 0. In LRU, we find the first position 0. In random, we just pick at random, right? So answering to these 3 questions, gonna give you the replacement policy. There are a bunch of different replacement policies, so like LRU and pseudo LRU are not the only ones. And then, by the way, you can just basically answer just questions. There are a whole bunch of different ways of doing this. There are adaptive methods that are actually being used a lot in modern systems. There are hybrid methods. That's kind of like if you have a bunch of different solutions, but you're not sure which one is doing better, what you can do is that dynamically you can switch between them. So many modern systems are actually using some form of hybrid method for choosing which sort of replacement policy to use. And then important things I wanted to note and point out is that the goodness of replacement policy is also dependent on your access pattern. So for example, if you have an access pattern like this versus you have an access pattern like this, different replacement policies might do differently in these cases, right? So replacement policy is not always the same. It doesn't have the same performance over everything. But of course, what we are interested in is the average behavior, right? So if you have the average behavior and you can do well in an average behavior, then you're good to go for a general purpose CPU. For high-end CPUs, that's why we have this hybrid methods, where if your workload is kind of changing, then your kind of replacement policy can also adapt. So these are like, very high-end sophisticated processors have these kind of adaptive methods in order to kind of fix this. I'm not going to go through the details of those more modern systems because this is like a advanced topics that you're going to see in other courses if you take the advanced computer architecture or the other course that they have. But yeah, if you're interested, you can definitely read more about there are things like drip and rip and BIP. These are kind of like advanced types of replacement policies that many modern systems use. But pseudo LRU, honestly, most of devices just use pseudo LRU. So that's why we just talk about that. Maybe in your project, I ask you to do like one of those more advanced ones. Who knows? Yeah. No? Any other questions? One last thing about replacement policy is the impact of replacement policy in AAT. Which one do you think, like which part of AAT is impacted by replacement policy? Anyone wants to answer this? Does the replacement policy change hit time? Yes? Why? So because how we update the hit time might change, but no, because as I told you, the hit time happens, like the update happens in the background. So hit time doesn't change. What about miss rate? Miss rate does change, right? So that's actually the part that we care about. And the miss penalty, of course, doesn't change. So your replacement policy is going to help you with the miss rate. And that's why it's important to have a good replacement policy. Okay? Let's have a quick break, come back, and then like takes like 3-4 minutes break, and then we're going to continue talking about this. All right, let's continue, guys. All right. So to kind of understand the impact of replacement policy in your AAT, you also need to understand the different types of misses that we're going to have. Because some misses are not necessarily going to be impacted by replacement policy, but some others will. Essentially, we're going to have 3 types of misses, okay? The first one is what we call a compulsory miss, okay? The compulsory miss is that the first time we see a data, okay? The first time that we see the data, it's guaranteed that it's going to be a miss, right? And we call this a compulsory miss because we haven't seen this data before. There's no way that we can fix this issue. Doesn't matter how big is your cache. Doesn't matter what sort of replacement policy you're going to use. Whatever you do, you never can get rid of compulsory misses. Okay. The second type of miss is what we call a capacity miss. The capacity miss is type of misses that it just happens because you have a small cache. Okay. So basically, capacity miss is defined as the misses that you would see even if you had a fully associative cache. Why? Because fully associative cache is the one that in terms of optimized use case of your cache. If it doesn't fit in your fully associative, it won't fit in direct map, it won't fit in set associative, right? So if the data is a miss in fully associative, we call this a capacity miss, okay? And then finally, we have what we call a conflict miss. And this conflict miss only happens in set associative or direct map. And these are the misses that wouldn't have happened if we had a fully associative cache. Okay. So replacement policy in some sense can help us with some form of capacity and some form of conflict miss. And the difference between fully direct map and set associative is basically helping with your conflict miss, right? And compulsory miss is none of them, neither using direct map or fully associative or set associative, nor using bigger cache can help you with compulsory misses. Okay? So there are what we call 3 C's: compulsory, capacity, and conflict. And the difference is just as you can see. And then your misses is a combination of these. Of course, all of your data sets we're going to have compulsory misses. If the data set is kind of a streaming data set, which means that you don't really re-reference things. You just goes from 0, boom, 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 all the way to the end. You don't re-reference things. That's when you're going to have lots of compulsory misses. Okay. So for example, graphs, machine learning applications, these are all compulsory misses, lots of them. Because for example, you read your data, and then you read another data, and you read another data. You don't really use them over and over again, right? We call this thrashing or streaming data, and they're not great for our caches. But the things that are being re-referenced over and over, these are the things that we can fix them by using a better replacement policy or better size of the cache and so on and so forth. And then another thing is that if the data that you're loading is bigger than our cache, then we also not gonna have a good performance. So for example, if you're loading 1 gigabyte of data, it obviously won't fit in your cache. But if you had a bigger cache, it would have fit, right? So these are kind of like the questions that we are looking at, the trade-offs that we are seeing in our caches. Okay. So now for the rest of this lecture, I'm going to talk about how do we optimize each of these different elements in our cache. Okay. So we have hit time, we have miss rate, and we have miss penalty, right? So we kind of casually talk about some of them. For example, I told you that, look, replacement policy helps you with miss rate, but let's systematically looking at each of these and see what are the options that we use in order to improve this, okay? So I don't think we can finish it at the end of this lecture, but hopefully by middle of next lecture, we can finish talking about it. So this is like adding pipeline to your baseline. So we kind of now understand the baseline of the cache. Let's talk about these optimizations, okay? So let's first talking about reducing miss rate. Miss rate is the one that you can do a lot of things. The first thing that we do is the notion of what we call block size, okay? And in order to reduce miss rate, we need to increase our block size, okay? So what is a block size? Basically, the idea of block size is using and exploiting the spatial locality in our design, okay? Think about the library example that I gave you. I told you that, for example, if I go to my bookshelf, instead of only bringing one book that I'm going to use, maybe I bring 3 books with me, right? Or think about arrays or integers and so on and so forth. So if I access A0, maybe it's a good idea to bring A1 and A2 and A3. So instead of bringing 1 byte and storing 1 byte per line, why don't we actually store multiple bytes per line? So instead of calling it a byte, we call it a block, okay? So we increase the block, and by increasing the block, potentially we can use more spatial locality. So potentially we can reduce the miss rate, okay? So instead of assuming that, so far we assume that there is only 1 byte per row. So for example, if I showed you this kind of like 8-row set, 8-row like fully associative cache, don't use notability, guys. It's not working. Used to be good. So what used to be 1 byte per row is now multiple bytes per row, and we call it a block. So each row is not storing 1 byte anymore, storing multiple bytes, and we call this a cache block. Okay. So now there's a big question that comes into the mind, and is that how do we do the addressing? So the addressing works this way. So first of all, we always need byte addressability in our memory, right? But if I store things in block level, then I need to also be able to kind of find the byte that I want within that block, okay? So if my block, for example, is 8 bytes, okay? Each row in the cache is 1 block, but I still need, for example, to read this particular byte out of this, okay? So that's where we introduce the idea of what we call block offset, okay? So the block offset is this number of bits that we use in order to decide which byte out of that block we are taking out, okay? Why do we need that? Because we always need byte addressability in our systems. So our addresses are 32-bit data, right? That each address is pointing to 1 line in the memory, and in the memory, each line is 1 byte. But in cache, we are we create a bundle of these bytes together. We call that a block. But since I still need to find the byte that I want, I will have to use this concept called a block offset. Okay, so my cache address, excuse me. My cache address, which used to be index and tag, is now block offset, index, and tag. And the block offset is basically telling me which of these, within each block, which of these addresses I need to go and check, okay? To give you a little bit more detail, this is basically how we structure our, for example, direct map cache. Let's say we have a 32-bit data. This is our memory address register. So let's say, for example, I decide to have blocks of size 8 bytes. So within 1 block, I have 8 bytes, okay? Previously, I had 1 byte in each block. Now I have 8 bytes within block. So as a result, I need 3 bits to offset through that block to find the byte that I want, right? So I go through that block, and for example, if this one is 0, 1, 0. This is the second block. So this is 0, 1, and 2. So this is the one that I'm going to select. Okay, so this is the block offset. And as you can see, the block offset is basically coming down here and it's going to be selected here. So this address here goes to this mux here. Then the rest is the same thing that we had before. So for example, this is an 8-row direct map cache. So you see that there are 8 rows. As a result, I'm using 3 bits for the index. And this is the 32-bit data. I use 3 bits for index, 3 bits for block offset. That remains 26 bits for my tag, right? 32 minus 3 minus 3, that would be 26. So the tag store will be 26, okay? So I have 8 rows, as you can see here, 8 rows, okay? Each one has a 26-bit tag. Then each one has 8 blocks, sorry, 1 block. Within 1 block, we have 8 bytes, okay? That's 1 row of my cache. As I said, I call this a set, okay? So now my set contains 8 bytes, okay? How do I select my data? As I showed you before, I first go to the index. The index basically select which row I want. For example, let's say I want this row. I go through this tag store. I bring this tag store and check it with the tag of the address. If these two matches, I call that a hit or miss. And then I bring that data. Let's say this is the data I selected. I bring that data to this buffer here. But within that buffer, I only need 1 byte of data because I always access 1 byte at a time. So that's where this block offset is going to help me to select which one. For example, if I want this one, I select this one, and this is the byte that I'm going to read. So at the end of this process, I'm going to read 1 byte and 1 byte only, but this is the way I'm going to select that byte. Does that make sense? Yeah. Say it again.
Like, don't we need to read 4 bytes at a time?
The question is, do we need to read 4 bytes at a time? You can read 4 bytes at a time, but essentially what will happen if you need 4 bytes at a time is like you select 4 of them. If you need like 1 of them, you remember you have like LW, LB, L, you know, we have different types of Ls, right? So if you had LB, which was 1 byte, then you select 1 byte. If you had LW, which was 4 bytes, then you'll read 4 bytes. You have the all 8 bytes if you want to, so you're good.
So for LRU, are you going to be stepping into each block and checking each address individually?
So the for LRU,
Yeah.
for LRU, you do so for cache in general. So the question is, what do we do for LRU when we have this block? So everything at the cache level happens at the block level. So for LRU, we have 1 block as 1. So basically each row has only just 1 position. So for all of my 8 bytes, I just have 1 position. So essentially the idea is that I'm not changing the structure of my rows. Still I have rows and columns. But what I'm saying is that now each row store more data. So instead of 1 byte, now I'm storing 8 bytes. Yes, a hit is anything in that block. And a miss is neither of them is actually what I want. But the beauty of this is what? The beauty of this is that let's say I have 8 blocks, okay? Sorry, 8 bytes within the block. So now my address 0 to 1 and then 2 and then all the way to 7, they all map into 1 block, right? Because now I store 8 things together. So if I have a sequence like this, what used to be miss, 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 now it's going to be the first one going to be a miss, but now I'm going to bring the entire block. So not only I'm bringing 0, but also I bring 1 and 2 and 3 all the way to 7 with me. So now the next time I read 1, this would be a hit because I already have. All right. So this is the structure of direct map. By the way, this is a 64-byte cache. Why is it 64? Because we have 8 rows, right? And then each row is 8 bytes. So 8 times 8 times byte, we have 64-byte cache. Yeah.
What if there's like a conflict, like we did other bits?
So the question is, what if there's a conflict? So everything happens at the block granularity. So if you kick out the block, you kick out the entire thing. You don't like keep 7 and kick out 1. You just kick everything with block level. The idea though here is that you need block because you rarely just read 1 byte. You most likely read 8 bytes together or 4 bytes together. But yeah, everything at the cache level is at block rank. So whatever I said so far in terms of we have ways, we have rows, we have positions, we have flag bits for PLRU, all is happening at the block level. Okay.
Yeah, it's kind of the same question, but also just to check, each one of those, the smaller squares, like the ones with the dot in the middle, those are each still a byte. Like,
There's still a byte. So these smaller squares are still a byte. Good. Same thing can happen for a fully associative cache. The difference is that we don't have index. Still, this is an 8-byte block. So I still need 3 bits for my blocks, so from 0 to 2. But since I don't have any index anymore, my tag now becomes 29 bits. And then as you can see, since I don't have the notion of index, what I do is that I do 8 parallel checks. So as you can see, I basically checked 8 things at the same time. And then whichever is say yes, this is the one that's kind of basically select the buffer here. So I'm not showing the output here, but yeah, the output is actually here. So as you can see, if this is a match, we're going to select that and put that into this buffer. And it's still, for example, if I just need this block, this byte, I'll pick this byte out of this buffer and then put this into my memory data register. Okay. And still, this is still a 64 because still I have 8 rows. Each row has 8 bytes. Okay. And finally, if I have a 2-way set associative cache, again 64, what I'm going to have now is the same thing for block offset because it's still my blocks are 8 bytes. The difference is that now I need only 2 bits for index because I only have 4 rows, but now I have 2 different ways in that rows. And by the way, the whole thing is called a set. And now my sets are bigger because now my sets are 2 blocks, right? So the difference between set associative and the others is that my sets are now bigger. And then since I use 2 and 3, that remains 27 for the tag. So how do we actually select this? First, the index goes to select the row. For example, let's say that we are selecting this row. Within this row, we have 2 comparators for this way and this way. Whichever is selected, we pick that data and put it into the buffer, right? So between these 2 buffer, this one selects which buffer goes to the final buffer. Within that final buffer, whichever blocks that we need, whichever bytes that we need to select, we select it using the block offset. Okay, and still this is a 64-byte cache because we have 4 rows. Each way is 8 bytes. We have 2 of those, so each set is now 16 bytes. And then we have 4 of those, so we have 64 bytes. Okay. Any questions? Yeah. The question is, what are these 2 buffers? So we have 2 way. These are my tag stores. This is tag store for way 0. This is tag store for way 1. And I need to check both of them in parallel, right? So the tag comes here. I check the tag of this one. I check the tag of this one. Whichever is a match, then we select that one. Good. One thing to kind of also using this block offset is this notion of CBS. Essentially, this C is the size, the number of bytes per cache, B is the bytes per block, and S is the blocks per set. Actually, if I give you these 3 numbers, you can tell me which size, like which structure this is, okay? So this is just something for you to kind of take a look at. This kind of so for my fully associative, I only have block offset and tag. For my fully associative and set associative, I have these. So this is my direct map, and this is my set associative. So this is fully, this is direct map, this is set associative, and this is basically just a notation for you to remember, because sometimes we can just address the cache this way. Okay. Okay, so going back to the block, I said all of these things to just tell you that it's a good idea to have blocks, okay? But then the big question is, how big should be a block? For example, in this case, I show you an 8 byte seems to be a good block size, okay? So if the block is really a good idea, why don't we have like a 64 byte blocks, or why don't we have a very, very large block size? And the answer to that is block size at some point going to give us what we call a diminishing return. Because if you're bringing larger and larger block size, we're going to have this thing called cache pollution. Because, for example, I told you, if I read 0 and it's a miss, then not only I bring 0, but I also bring the rest of the block with me. So, for example, if this is an 8, I bring 1 and 2 all the way to 7. Okay, so I bring 8 bytes together. And now let's say my block size is 128 bytes, which means that instead of bringing only 0, I bring 0 all the way to 127. Okay, of course, if I use 0 to 127, that's a very good idea to do. But if I only use 0 to 8, those other things that I'm bringing, they're all junk. It's pollute my cache, right? So that's why if you think about the miss rate, if you think about the relationship between miss rate and block size, you will see that it's actually kind of like going down as the block size increases, but there is actually a sweet spot, and after that, not only your miss rate goes down, it actually goes up. And this is the area that we call pollution area, like cache pollution area. Question?
Is it possible to have different block sizes in different rows, or have changing block sizes?
The question is, can we have changing block sizes for different rows? We actually can, and we call that sub-blocking, and I'm going to describe it to you later. But it just makes things a little bit more complex. I mean, we generally have big blocks, but within those big blocks, we can have sub-blocks. So the big problem with the block size is it's not gonna, at some point, it's not gonna help you with miss rate anymore. Another big problem with block size is increasing your miss penalty. Why? Because you need to go a lower level, like, a level down and bring that data. Now I'm telling you that what used to be just 1 byte is now 8 bytes, or now it's 64 bytes. So of course your miss penalty increases because you need to bring more data up, right? So increasing your block size significantly may not help because it creates pollution, and in some cases it actually increases your miss penalty. One thing I want to emphasize though is that there is this notion or difference between what we call bandwidth and latency, okay? Latency, or in other words, miss penalty, is the time it takes for us to bring data from a lower level cache or lower level memory to upper level, okay? So for example, if I need to bring some data from here to here, the time it takes to bring that data, we call that latency or miss penalty. But there's also this notion of bandwidth, which means that how much data that I can bring, okay? So usually my bandwidth is not just 1 byte. My bandwidth is in order of hundreds of bytes, okay? In other words, one time bringing data versus multiple time bringing data is not a difference. If I have more bandwidth, I can bring more data with me with the same amount of latency. So there is a difference between latency and bandwidth. The difference is that if my bandwidth, for example, is 64 byte, it means that the latency for bringing 1 byte versus 64 byte is exactly the same, because it's just one-time thing I can bring. And think about it, it's like, if you have 2 hands, and in each hand you can bring 1 book, then your bandwidth is 2. So the latency for you to go to the shelf and bring in 2 books is the same as go and bring in 1 book. But the latency for you to bring in 3 books is not the same, because now you need to go one time, bring in 2, and then you need to go another time and bring in 1. Okay? So going back to this block size necessarily doesn't increase your miss penalty. It only increases your miss penalty when it exceeds your bandwidth. Okay? So usually if we have, for example, an 8-byte block, our bandwidth is well over that 8-byte. That's why bigger block size by nature does not change your miss penalty. It might if you go crazy on the block size. Okay. Cool. So that's the first thing. So remember that we are at this point where we want to optimize this, and for now we want to reduce our miss rate. The first thing I explain is that you can increase your block size. Okay. So let's see what other things exist. The second thing that you can do, and we already discussed this, is increasing your associativity, right? I told you that your fully associative in terms of miss rate is the best, and then your set associative, and then your direct map. Okay, so increasing associativity starting from direct map going toward fully associative can help you with improving your miss rate. In other words, decreasing your miss rate. Okay. Another question, of course, is why don't we, increase our ways as much as we can? So, for example, I told you that most systems either use 8 or 16 ways. So why don't we do 32 or 64? Similar case to cache pollution, we're going to have what we call diminishing returns, which essentially what will happen is that at some point, doesn't matter how many ways I have, what I'm going to have is conflict misses and compulsory misses. Okay. Remember that I told you that compulsory misses and conflict misses doesn't matter which sort of cache you're using. It's because of the size and type of the data that you have. So increasing the number of ways won't help you with that. That's why at this point here, doesn't matter how much more ways you're adding, your miss rate does not go down. It stays the same. It doesn't go up either because nothing bad will happen. It just stays the same. The only bad thing that happens is that increasing the number of ways, as I told you, will increase your hit time, right? Because you need to check more things at the same time. So it increases your hit time. So you want to kind of find a good balance between the hit time and the miss rate. That's why you don't want to go really, really high in terms of your waste. Okay, so that's why usually 8 or 16 is the sweet spot in most of the systems. Okay. Any questions? Cool. The third things that help us with miss rate is, of course, larger cache size. The bigger the cache, the better our system is. Okay. In terms of miss rate, more things to store, of course, there is more chance that I have that data in my cache, right? Pretty intuitive. Again, there might be a question of how big is the cache? Why don't we go crazy with the cache as well? And then again, you have to look into that 3 types of misses that I told you: compulsory, conflict, and capacity. Bigger cache helps you with conflict and capacity, but it doesn't help you with compulsory misses. Okay. So again, at some point, we're going to have diminishing returns because most of your misses is going to be compulsory misses. Again, for example, something like a graph or a neural network behavior that's kind of streaming through your data, doesn't matter how big is your cache, you never can actually fit the data that they want in your cache. Okay. Another problem with larger caches is that larger caches increase your hit time, because essentially the way that we create our SRAMs is dependent on how many rows. If we increase the number of rows, the time for us to kind of decode the data takes a little bit longer. Okay. And as a result, our hit time increases. So a bigger cache, unfortunately, results in lower hit time. And if I'm not really gaining anything from increasing my size, it's not a good idea to increase my size. Okay. So in other words, for larger caches, double the size does not mean double the performance. So your AAT is not going to be reduced by half if you double the size, because at some point it's going to become flat. Okay. So what should we do in those cases? That if the cache size doesn't help us, what else can we do in order to reduce the miss rate? And that's where the idea of prefetching comes into the play. So I told you that, for example, if something is streaming, if I'm doing 0, 1, 2, 3 all the way to, I don't know, thousands or millions, and I'm not really going back to any of them, can I somehow predict this behavior and do something about that? And that's where the idea of prefetching comes. And then basically the idea is this, that if I can guess the access pattern, I can actually prefetch, in other words, preload my cache with the future data. Okay? So for example, consider in a sequence like this, and by the way, this is a very frequent sequence. Think about all your for loops, and then you do like for I equal to 1 to, I don't know, 100, read AI, which is your, for example, your matrix or whatever, and then write that AI into something. So this is basically, in terms of cache access pattern, you're doing something like this, like you're accessing address 0, then 1, and then 2, and 3, and so on and so forth. So if I can actually predict this, I can once I see this, I can bring this, and then I can bring this, and I can bring this. With block size, we're somehow addressing this, but with block size, I cannot bring more than the block size. But what I'm proposing now is that if I'm sure that I'm going to access all of these things one after another, why don't I bring more things with me? And this is what we call prefetching. We prefetch the data to the cache, even if the processor hasn't requested this. So this is just internally created by the cache itself without even being requested. So we kind of like, prefetch, in other words. Okay? So how does prefetch help? Prefetch reduce your compulsory misses, right? Because now I know that if I bring I1, I2, and I3, then the next time I accessing I3, even for the first time, I already have it in my cache. So I can reduce and eliminate compulsory misses ideally if I do a good job in prefetching. Okay, but of course, prefetching has its own downsides, and generally, all of these methods that I'm talking about, they all have trade-offs. Okay, there is not one that is always good, and there is not that one that is always bad. There's always trade-offs, so you kind of you have to pay attention to this trade-off. Same thing for prefetching. So for prefetching, the trade-off is same story with block size. I can pollute my cache if I'm bringing junk, right? So if I'm predicting that I'm going to access I plus 1, I plus 2, I plus 3, I can prefetch it. But what if I'm not really, after I2, I decided that I'm accessing I plus 100, for example, right? So I brought I3, but I'm not going to use I3. So I just kick out something that might have been useful, right? So cache pollution, same as the block size, is a big problem in prefetching. It could be useful if you're accurate, but it may not be useful if you're doing cache pollution. Okay? Question?
How is this idea different from like the block size where we're also bringing it?
So the question is, how does this different from blocking? So blocking is kind of deterministic. So for example, if I have 8-byte block, if I see the first byte, I'm going to bring the other 7. The prefetching is more complicated than that. So for example, let's say if I do +2 so it's like we're doing it in its stride, I can have a prefetcher that kind of predict that. So if I bring the first 8-byte, I might skip the next 8-byte and then bring the next, if my pattern is like that. So so in some sense, prefetcher is much more glorified version of the block sizing. How do we implement block sizing? So prefetching. So there are 4 questions that you need to answer. The what is basically what should we prefetch? Obviously, that's the big question. There are various different things. We usually do what we call a next line prefetcher, which we just predict the next line. And as I said, this is very, very common because there are lots of these for loop and while loops that just do I plus 1, I plus 1, I plus 1. So what address we need to prefetch is a big question that we need to answer. When do we prefetch is another big question. When should we bring the data and put it in the cache? Should we do it way before when we anticipate that there's going to be data? Should we do it just in time? What should we do in terms of that? And then the third question is where? So that if I want to prefetch, should I prefetch and put it into my cache? or should I have a separate kind of buffer for prefetching? Which level should I put it? How should I promote it? Should I put it as a least recently used, most recently used? These kind of decisions, and then basically how the prefetcher operates. Is it a software-based prefetcher? Is it a hardware-based prefetcher? Is it a combination of those two? These are the questions that state of the art. There are lots of research about this of each one. Two quick examples. The software prefetcher is actually, it's literally in software. You actually use some instructions to prefetch things. An example of this is something like this, that you can literally, for example, you have a for loop. You can actually have, for example, most of these operating systems supports this. Most of these programming languages support this. You can say, for example, prefetch I plus 8. Because what I do is that I jump with like 8 byte, 8 byte. So I can actually tell the processor that this is the algorithm I'm using, go and prefetch. So actually the programmer can actually tell this to the CPU. Or for example, if I'm using some form of pointer chasing, that is kind of like doing some irregular access pattern, I can also tell the processor that the next one is at this address, go and prefetch it for me, okay? So at the software level, I can do this. At the hardware level, I can also do this. The simple thing that we do is that we look at the address, and if I see, for example, 3 consecutive addresses, the fourth one is the one that we're going to predict. So if I see I and I plus 1 and I plus 2, then I'm going to prefetch I plus 3. So I'm kind of like having a history of the last 3 addresses. If the distance between these 3 is 1, then I'm going to prefetch the next one. If the distance between them is 2, I'm going to prefetch the next 2. Yeah.
The pointer-based prefetching, previous slide,
Mm-hmm.
how would that work? Would it need to like first read the address of the pointer and then like read that next address for the prefetch?
Yes. So we have that address here. So the question is, how does this work? So in your program, you have that address. You don't have the content, but you know the address, right? So what you do is that you have already prefetched the previous one. So this one is the previous one. And now you're telling your CPU to go and find the next one that in the next iteration of the loop I'm going to use and prefetch that. So by the time that I'm doing this and coming back, now I have the data already. So it happens in the back.
Is that possibly like a less efficient array prefetch because the pointer addresses might not be continuous?
Why should, I mean, it doesn't matter to be continuous, right? That's why you actually use this address. So this could be like one time could be 100, the other time could be 522, for example. I don't know. Could be any random number, right? You exactly know what that address is. That's like at your program, you have that content because remember, like if you have a pointer, you always have the pointer to the next block, right? So you have that number in this iteration. So you know that address, you tell the CPU that this is going to be the next block I'm going to use to go and grab it for me while I'm doing the analysis on the current block, right? So you're kind of working on this, tell the CPU that, okay, the next block will be that one. The CPU in the background going to bring that data while you're also doing your analysis in the current block. Next time you come back, that's the next block is already ready for you, right? So that's how you're actually going to improve this. Question. All right. So let me finish this. So there's all, there are lots of different, ideas in prefetchers. If you're interested, definitely go and take a look. And as I said, prefetching is helpful for reducing compulsory, but it's bad for your cache pollution. Okay. So let's pause here, come back, and then continue this next time.
In this diagram, what is MDR?